Hi everyone, this is MathsForUni. This is question 8 from lecture 11 from our Udemy course, Bridging the Gap to Maths at University. If you find this content helpful, then please consider liking and subscribing, as well as checking out our full Udemy course. The link is in the description. The question says, what are the real and imaginary parts of the complex function f of z equals z squared, where we write z equals x plus iy, so that the real part of z is x and the imaginary part is y. How about doing the same for g of z equals sine of z? You might not have seen the sign of a complex number before. It asks us to write our answers as functions of the two variables x and y. First, let's begin by briefly discussing complex functions. For example, in proper function notation, the function f of z equals z squared looks like f being a function from the complex numbers to the complex numbers, with z being sent to z squared, i.e. this function has a complex number input z and a complex number output z squared. For example, what is f of 1 minus I? Well, this would be 1 minus I all squared, and then 1 squared gives us 1, 1 times minus I twice gives us a minus 2i, and then a minus I all squared gives us a minus 1, and so we get minus 2i. For this function, we write out the input z by separating out its real and imaginary parts. We write z equals x plus iy, where x is the real part of z and y is the imaginary part of z. For the above example, we have z equals 1 minus I, and so x would be 1 and y would be minus 1. We can try and do the same as we've done here with z to the output of the function by separating its real and imaginary parts. Let's try and do this for the first complex function, f of z equals z squared. By writing z as x plus iy, we get f of z equals z squared, which is x plus iy all squared, and then we expand to get x squared plus 2ixy, and then we have a plus iy all squared. The iy all squared will give us a minus y squared, which is real, and so we get x squared minus y squared as the real part, and then plus I with a 2xy as the imaginary part. Then we can do the same thing for g of z equals sine of z, trying to find a real part and an imaginary part. Again, we write z equals x plus iy, so we get sine of x plus iy, and then we use the trigonometric addition formulae to split this up as sine x cos iy plus sine iy, and then a cos x. Then, to get the real and imaginary parts, we need to understand these sine of iy and cos of iy. To do this, we use the trigonometric formulae in terms of complex exponentials. In particular, sine of theta is equal to e to the I theta minus e to the minus I theta divided by 2I. Cos of theta is similar. We have e to the I theta plus e to the minus I theta divided by 2. These results come from Euler's formula, if you're not familiar, which is e to the I theta equals cos theta plus I sine theta. If we put Iy in place of theta, everywhere we see a theta in these results, then we have sine of Iy is e to the I Iy minus e to the minus I Iy, all divided by 2I, and then we have these I times I giving us an I squared, which is minus 1, and so we have e to the minus y minus e to the y over 2I. Then we can bring this I to be up here, which gives us a minus sign, so we can put the minus sign and flip these two things around, giving us I multiplied by e to the y minus e to the minus y divided by 2. And then we recognise this expression here as the sine of y. So we have I sine of y, which is the hyperbolic trigonometric function sine. Similarly, doing the same for cos, and I'll leave it as an exercise, this ends up giving us cos of y. There's no I involved here. In particular, the hyperbolic trigonometric functions arise as the standard trigonometric functions with imaginary inputs. If we put these results into the above that we have here for our g of z, then we get g of z is equal to sine x cos y plus I cos x sine y. This tells us that the real part of g of z is sine x cos y, and the imaginary part is cos x sine y. If you found this content helpful, then please consider liking and subscribing, as well as checking out our full Udemy course. The link is in the description. Thanks for watching, and goodbye for now.